Good afternoon, class. I am doing this recording on redox reactions after having marked the tests. So just want to kind of focus on some of the things, the common mistakes that were made, and making sure that the concepts are clear. So I will be looking at the electrochemical series first in the data booklet and explaining that, and then I will hop into some equations that you had on the test that were not done so well. So explaining those, and hope to clarify some of the misconceptions that just came out of that test. So starting with the electrochemical series, what I'm recording here is some of the annotations that I asked you to make on the electrochemical series to quickly identify redox reactions that will spontaneously happen. So redox reactions, what does spontaneous meaning they will naturally occur. The exchange of electrons where oil rig will help us to identify that oxidation is loss of electrons, while reduction is gain of electrons. So keeping that in mind, the oil rig acronym, just to remind us of what we are looking for. Your oxidants are going to be here. Oxidants are on the left hand side of the equation. So every equation will have the oxidant on the left hand side and the reductants will be on the right hand side. So your reductants will be here. Might just try and make that a little bit neater. So your reductants are here. And your oxidants are going up this way. So your strongest oxidant is here on the left hand side on the top. Oxidant, and your strongest reductant is right at the bottom here. What I'm also going to make a note here is that reductant undergoes oxidation, and oxidant undergoes reduction. A bit of the confusion that always will occur in your heads based on oxidation, reduction, and what type of reactions will take place for each of those. So your oxidant on the left hand side of the equation, reductant or its conjugate reductant will be on the right hand side. So if you are looking at a half cell, your half cell will be one whole equation on one line. That's your half cell. Now, the spontaneity of the reaction, meaning the spontaneous reactions will be happening only when your oxidant sits above your reductant. So look at me writing this equation where your oxidant is on the left hand side above the reductant, which is on the right hand side. And your reduction reaction will go this way where oxidation happens. and your oxidant reaction will happen going towards right, which is your reduction reaction. So you're going to have electrons here, whilst in the bottom equation, the electrons will turn up because it will be loss of electrons. So they will be basically giving up electrons. And what you're taking note of is that the spontaneous reaction will be the reductant undergoing oxidation and the oxidant undergoing reduction. So your inverted Z. That inverted Z is your spontaneous reaction. So your reductant here and your oxidant here. And reactions going this way. So taking note of these little things on your electrochemical series will help you to identify spontaneous reactions. So whenever you get given an equation, just make sure you mark the species or the oxidant and reductant that are present. So if I'm putting aluminium, solid aluminium, in, let's say, a solution of tin, then that's a spontaneous reaction, which means a reaction will take place and aluminium will dissolve to form aluminium ions, and the tin ions will actually gain the electron or grab the electrons and turn into tin solid. So that's a spontaneous reaction right there. Now I could have the two half equations in two separate cells and make a galvanic cell out of it, which you should be practicing with the different equations over here. Now hopping into, I'm just going to get into the equation that was not done so well in our test. So let me just grab that. Give me 1 second to just open up that equation for us so we can address the particular equation. This was the hydrogen sulfide one. So there were two equations given. You were supposed to derive from the half equation or two chemicals that were changing in a redox reaction or an oxidation reaction, and identify the chemicals that were changing using KOHES. Now, I'm going to just elaborate on that KOHES bit because we need to, I'm just going to draw some lines here so it's easy for me to write stuff. Now, what does KOHES stand for? K is for key element. Other than hydrogen and oxygen. O is, so the very first element that you will balance on the two sides would be the key element. After that, you would look at the oxygens on both sides and see if they are not balanced. You need to balance them using water. So oxygen is balanced on opposite side using water. So you'll add water on the opposite side of where there are less oxygens. Once you've added the water on the opposite side, the next element that you would balance is hydrogen. So because these reactions are under acidic conditions, add H plus ions on the side with less hydrogen. Okay, so you'll add H plus ions, and then you would balance the electrons, or you would actually add electrons to equate the charges on both sides. So add electrons, the negative electrons, on the more positive side, to balance or equate charges on both sides. So the more positive side has got a higher positive charge, and you want to bring it down to the same charge on the opposite side by choosing to add a certain number of electrons. And then the last thing you will do is add states to all species except electrons. Electrons don't get states. Yeah. So you'll add ions, will have aqueous state, and of course solid metals will have a solid state. Pure water has a liquid state. So these are the three states. And of course, if it is a gas, you would just use G for gas. And G gases are used with a state of G. So taking note that ions will be aqueous, solid metals will be S, pure liquids will be L, like water, and gases will have a G state. So the things that you're looking at here is your key element, your oxygen, then your hydrogen with hydrogen ions, then your electrons, and then your states. These are the things that you have to take care of. So the equation in the test question was, it was question number 4A, test question. You had H2S was turning, this is a gas, was turning into SO2 gas. So you're going to have to balance this equation. This is not balanced. So you're going to start with your key element, which is, I'm just going to use a different color here. Might use yellow. So your key element is sulfur, which is not hydrogen and not oxygen. So you have one sulfur on the left-hand side and you have one sulfur on the right-hand side. So your sulfurs are really balanced. So you don't have to do anything to change that. The next element that you have to balance is your oxygen. There are two on the left-hand side, but none on the, on the right-hand side and none on the left-hand side. So what you're going to do is add waters. So add your water to the opposite side to balance out the oxygens. So I need two oxygens on the left-hand side. So what I'm going to do is I'm going to reduce this arrow so I can add all the things that I want to add. So I'm going to add 2 waters. Okay, so this is liquid. I can do it along the way or I can do it at the end. Now, the hydrogens that I have on the left-hand side are, let's use this color for hydrogen. I have 4 hydrogens. 2 times 2 is 4 and another 2 here. So I really have 6 hydrogens. 6 hydrogens here. And on the right hand side, I have none. So what am I going to do? I'm going to add hydrogen ions, and a lot of you were making mistake here by not adding the plus charge on the hydrogen ion. So you want to make sure that you do that. So what's happening on the other side, on the opposite side of where the hydrogens are, I'm going to add 6 H pluses because there are 4 plus 2, which is 6 hydrogens. Now, the last thing that I will do, because I've already done my states, I'm also going to write aqueous here because ions are always aqueous. I am going to add electrons on the more positive side to balance or equate the charges on both sides. I should have written the word both here, so I'll just add that on both sides. So if I want to equate the charges on both sides, I have 6 plus charges here and none over here, 0 charges. This is hydrogens. Okay, so I have 0 charge on the left hand side. The more positive side is 6 plus. How do I equate the charges? I need to bring the charges down to 0 because that's got the smaller charge there. So basically just add 6 electrons to the right hand side. And what do I see here? That electrons are being lost. And what is loss of electron? It's oxidation. It's oil rig. So this is oxidation reaction because electrons are lost. That's how you balance your equations using KOHES. Now the second equation in the test was given to us as V2O7 4 minus aqueous turns into VO2 plus. I'm actually going to do it in a little bit better way here. I'm going to show you how you should start with this equation, which is basically write your chemicals on both sides but leave enough space for the KOHES. So I'm going to go VO2 plus aqueous. Now, the very first thing that I'm going to do is the key element. The key element is V, vanadium. So if I'm going to use a colored highlighter for that, I can see that I have 2 vanadiums here and only 1 on the opposite side. So basically I'm going to add a 2 as a coefficient because that's all I can do. I cannot change the formula, remember. I have to change the coefficient. So I add the 2 as a coefficient for the vanadium oxide 2 plus on the opposite side, balancing out my vanadiums now in that first step. My second step is to look after the oxygens. Yeah, so I have 7 oxygens on one side, and on the other side, by adding the 2, I really have 2 oxygens. So I have 7 on one side and 2 on the other. I'm really short of 5 oxygens on the right hand side. So I'm going to add 5 waters for that to compensate for the 5 oxygens that are short on the right hand side. Okay, so my next step is the H plus ions or the H hydrogens that I have added, yeah, on the right hand side. I want to kind of take care of the hydrogens, and I'm going to replace them on the opposite side by H plus ions which come from the acid. These redox reactions take place in acidic medium. That means there has to be acid present in the solution, otherwise these redox reactions cannot take place. So I have 10 hydrogens here on the right hand side. So I'm going to write that down. I have 10 hydrogens on the right hand side, but none on the left. So I'm basically going to add 10 H pluses on the left hand side. Now the hydrogens are balanced. So 5 times 2 is 10 on the right and 10 on the left. My next step is electrons. I'm going to add electrons to the more positive side to equate the charges on both sides. So let me firstly count how many charges I have on the left and on the right. What I can see here is I have 4 negative charges here and 10 positive charges, which is equal to 6 positive charges on the left hand side. On the right hand side, I have 2 times 2, which is 4. So basically that's 2 positive charges, but I have 2 of those molecules, and therefore my positive charges are plus 4 on the right hand side. How do I equate these charges from 6 plus to 4 plus? The more positive side is on the left hand side, so I'm going to add 2 electrons. A lot of you were making mistakes here. Take note, I'm adding 2 electrons so that this becomes 4 plus, and then it will equate to the 4 plus on the right hand side. And that is my balanced half equation of this particular species. And what I can see here is this is rig. This is reduction is gain of electrons. So these electrons are being gained by the species. So therefore this is reduction. So I hope this actually answers your questions. If you are not so sure about these, can you please come and see me when we get back? Redox reactions are very important for next year as well. So I'm going to stop recording this. Practice using KOHES, using all the textbook questions and any worksheets that I'm giving you.